Hello, everybody. So we are Team Lumos, and in this presentation, we're going to walk you through how we build camera-based autonomous car prototype. So the prototype itself was initially designed for Capstone design course. So in this presentation, I'm going to give you a quick introduction to our problem statement and project goals and our value proposition. And then we'll walk you through our system overview and then camera-based perception models, lane detection module, inference and control flow, latency analysis. And at the end of the presentation, we'll give our conclusions and future work. So there are a lot of scenarios where car accidents include unintended lane crossing or pedestrian collision due to late reaction, and sometimes even missed red lights. So the obvious solution might be a camera-based perception system that is built into our car, and then lane detection, object detection, and all of them are retrofitted on the existing vehicles. So our value proposition here is we'll be providing lightweight vision models, and we're going to see if those models work well on low-cost hardware. In this case, we use Raspberry Pi and cloud and real-time latency feasibility. So this is basically our end-to-end architecture. We're getting a video input through our cameras into Raspberry Pi, and then forwarding these videos into our remote cloud core, or sometimes our own desktops. And then here there's a perception stack. After getting the inputs from the perception stack, we have execution layer, and then remote motion control. And all of this are again fitted into our Raspberry Pi to control the Turtlebot. So for Turtlebot, we put a front camera that covers 120 degrees, and we also integrated ROS2 node diagrams, and here you can see 3D visuals as well.
So for camera-based perception, we use YOLO V8 model for object detection. And YOLO V8 is a modern one-stage object detection model designed for high accuracy and real-time inference. It detects and classifies different objects in a single forward pass. So that's why it makes it possible for time-critical applications. That's why we used the YOLO V8 model as a baseline for our object detection model. So we decided to customize our YOLO V8 model for lightweight deployment by changing the backbone and the head of our architecture. So in the end, we achieved to reduce the number of parameters from 3 million to 1 million, which got 3 times smaller. For floating point operations, we got about from 9 million to 4 million, which is about 2 times faster. So for training setup, we got 20 object classes like pedestrians, vehicles, different type of vehicles, traffic lights and traffic signs, and different speed limits. So for our backbone, we decided to scale it by 2 for lower computational cost. When it comes to our head modification, we also scaled it by halving all channel dimensions and also enhanced it with top-down and bottom-up path aggregation network feature fusion paths, and also improving its multi-scale feature aggregation with lower computational cost. So this is the example inference result gotten from our model. Here, as you can see, it can detect different persons, vehicles, and different traffic signs. So also, we used lane detection using half transform, which gets the edges of the roads by using Canny edge detector, and also lining up all the edges and making it clear lane lines, which helps our autonomous vehicle to know which direction to go and control its motion. So this is the overall hardware and software pipeline by using Turtlebot setup in Raspberry OS using Ubuntu, and we also got VM setup on our desktop, and we got our connection for the network with SSH connection, and we optimized it. So for our software pipeline, we got pedestrian detection using deep learning model, and also traffic light detection using the same model, and also, as I said, using half transform, we got lane detection and road sign detection with our trained models. And this is the example system log output after we run our models and all the pipeline. As you can see, it can detect all the objects and traffic signs and traffic lights, as you can see here.
The decision making happens here in the execution layer. It uses a strict priority system. Priority 1 is for safety emergency braking for pedestrians. Priority 2 is for compliance, obeying the traffic lights and signs. Priority 3 is navigation for smooth lane following using PID control. For architecture, we engineered the software to be modular. Every perception model is independent, allowing for easy updates. Importantly, we automated the complex setup with shell scripts, allowing the entire robot to be launched in under 3 minutes. This is specifically made for Turtlebot with ROC2 for Linux laptops. Regarding the performance, we benchmarked 3 configurations. Our final setup, the Raspberry Pi 5 with remote laptop processing, achieved the best result, with a workable end-to-end latency of about 320 milliseconds. In conclusion, we validated low-cost autonomy by retrofitting standard hardware for optimized efficiency, making our custom YOLO models 3 times lighter. And we proved the viability with a stable modular ROC2 architecture that is ready for future development. Looking ahead, we plan to upgrade from this split compute architecture to a unified edge AI system using NVIDIA Jetson. This will eliminate network lag and allow us to replace basic line detection with advanced deep learning segmentation for curved roads. Thank you. That's the end of our presentation.